Hello friends, welcome to our video series of static timing analysis. Here in this lecture, we are going to discuss dynamic versus static timing analysis. Before starting the discussion, it is important to understand what timing analysis is. So timing analysis is basically a process of verifying that the timing constraint of a digital circuit is meeting or not. In a simple way, we can understand that timing analysis is basically performed to ensure that the circuit meets its timing requirement under all the conditions. We'll take a help of the circuit diagram as shown in the screen to understand and discuss what timing analysis is. So there are basically two-way or methods through which we can do timing analysis. We'll start with the method first. So the first way of doing timing analysis is to break the circuit into different paths and add all the path delay in that particular path and check whether the total propagation delay of the circuit is meeting a timing constraint or not. If not, then we'll treat it as a timing violation. So we'll start with the path one, which as you can see is starting from the input of our circuit and ending at the D pin of our flip flop. Similarly, there can be some other path, let's say part two, which is starting from the intermediate node and ending at the D pin of a flip flop. Same way, there can be some other path, part three, starting from the input, ending at some intermediate node of our circuit. But for our consideration and making and in keeping our consideration simple only, we'll treat path one only in our timing analysis. So as you can see, we have calculated the path delay with respect to the path one, which is starting from the input to the D pin, which comes out to be 8 nanosecond. So tool will check that whether this 8 nanosecond is within our timing constraint of path one or not. If not, then we'll treat it as a timing violation. Then there is one important question that should come into mind, that these delay that are mentioned on the gates, from where and how they are coming. So the answer for this is liberty file. So this liberty file is basically given or created by a PDK team, or you can just say that it is created by a person who designed these standard cells. So it's analyze these standard cells using a space model with some input transitions and some output load or some fan out, and check what delay that those standard cells or those gates are giving, and it form a combination of these transition and output load, and check what respective delay they are getting and put it in a form of a lookup table, and that lookup table is stored in liberty file. So tool basically goes into this liberty file and check what is the respective delay to the standard cell with respect to the load and the input transition it is seeing. There are various parameters that are also included in the liberty file, like cell name, input transition time, output load capacitance, delay time, transition time, pin to pin delay, setup and hold timing specification of that standard cells or flop, and a lot more. So tool will basically go and check for the cell name in the lookup table and extract out the desired delay with respect to the input transition and the output load, and use that delay in calculating the propagation delay of that circuit. Similarly, there are these net also which are present in our circuit. But for our part delay calculation, we haven't taken the net delay into consideration. But in actual analysis, this net delay also comes into picture. So there are like two way we can through which we can calculate this net delay. One is through wire load model. Another one is the RC load extraction. So we all know that wires are nothing, it's just a bunch of RC circuits stacked together in a series. So these RC circuits basically will give some kind of a delay, which is in the form of a tau, which is equals to RC. So that delay will also should be computed while calculating the propagation delay of a path. Now, the second method of doing the timing analysis is to provide some kind of input vector or input stimulus at the input of our circuit and checking what are the output we are getting. And if those output is exactly equal to the expected output that we want, then it is fine. Otherwise, this is also treated as a timing violation. So these are the two way through which we can do timing analysis. Here, we're easily able to do timing analysis here in this circuit manually because the circuit is very small. But we know in actual digital design, the circuit is not this much small. And in today's era, we know that digital circuit has reached to 7 nanometer, 5 nanometer, and even a lot of companies are now working in 3 nanometer also. So the digital circuit is very complex and it is very tedious or even impossible to do these kind of timing analysis manually in those kind of complex digital circuit. So for this, EDA tool comes into picture. So a lot of EDA company design STA tool to do similar kind of analysis, but in a automated way. So we'll take a look of. S- so we'll go to the difference of static and dynamic timing analysis and take a look how these are done and what are the difference between them. So static timing analysis and dynamic timing analysis is nothing. It's just the two methods that we have discussed in the previous slides. A lot of EDA tools are doing STA timing analysis and dynamic timing analysis. Some example you can take like Tempest of Cadence is one predominant tool used in the industry for doing STA timing analysis. Similarly, Model Sim of Mentor Graphic is used for dynamic timing analysis. Now, we have already seen the first method of doing timing analysis where we were just checking every path in the design for timing violation. It is nothing, it's just a static timing analysis tool is doing for us in an automated way. In dynamic timing analysis, we are just applying the input vectors and checking what are the correct output vectors to to respect to the particular circuit. The other important difference between dynamic and static timing analysis is that static timing analysis doesn't verify the functionality. And that is easily understandable because static timing analysis doesn't have intelligence or doesn't know about the circuit functionality or behavior. All it does is to break the circuit into different possible path and check whether that delay of those paths are coming at the right time, or you can say it is meeting the timing constraint of that path or not. So SCA does not check for the logic correctness of the design. On the other hand, dynamic timing analysis verify the functionality because here we are applying the input vector and checking the corresponding output vector related to it. So it checked for the functionality. One important difference is that static timing analysis is faster. And the reason is simple because it doesn't have to do any functionality check. All it has to do is to check whether the path, all the path in the circuit are meeting the timing constraint or not. So this makes it possible for the designer to experiment different synthesis option and constraint in a very shorter period of time. But this is not an option here in dynamic timing analysis because tool has to do lot of functionality check and it is quite slower comparatively to the static timing analysis. So dynamic timing analysis is time consuming. The other important difference is that, as we have already discussed while we are discussing the static timing analysis, that it breaks the design in all the possible combination of uh, different path. So it gives a good coverage because it checks all the path. So we'll able to know that which path we are violating and which path we are not violating. This is not the case with dynamic timing analysis because it has less coverage as it depends on the input or the test stimulus. So we know that with the now the circuits are very complex and have lot of input pins. So there will be lot of input combination that need to be applied to have a good coverage or 100% coverage, which will not be possible because with the growing test stimulus, the time of the stat of this dynamic timing analysis will also increase as it has to do a lot of functionality check. So we have to do some kind of a trade-off between the speed of dynamic timing analysis and coverage. The other important difference is that static timing analysis is little less accurate comparatively to the dynamic timing analysis. The reason is that it doesn't check for the functionality, and dynamic timing analysis is more accurate because it's checked for the functionality and timing both. One important advantage of dynamic timing analysis is that static timing analysis only do synchronous part of the design, that it check only the synchronous part of the design. So you can just say that it add the propagation delay along path between only clocked element or between two reg. But dynamic timing analysis do or check both synchronous and asynchronous part of the design. So whenever you want to check for asynchronous timing in our circuit, it is important to opt for the dynamic timing analysis. The other important difference is that static timing analysis cannot detect error related to the logic operation. This is not the case with dynamic timing analysis because input stimulus applied can detect timing error like race condition. And the reason is quite simple. It's just that designer know that what possible input combination can result to a race condition, and can just give it while doing dynamic timing analysis and check whether we are getting race condition or not. But this cannot be a feature for a static timing analysis because here we are not able to applying any here we are not applying any input stimulus in the analysis. Other major downfall of static timing analysis is that it can report some kind of a false error. And the reason is that static timing analysis doesn't have an intelligence about the behavior or the functionality of a design. So many of a time, there may be a chance that static timing analysis is checking for some path between two reg, and that path actually doesn't comes into picture when the actual chip is working. So there's no point checking for the static timing analysis there in that particular path, checking for the timing constraint for that particular path. So there may be a chance that tool can give some kind of a false error for those false path. So the reason for those false path or the potential to detect some false error exists since because the circuit behavior is not considered during the analysis. But in dynamic timing analysis, we don't have this issue because we are applying input stimulus and we know that what output stimulus we want. So these kind of false error will not get. But this issue in the static timing analysis can be resolved because a lot of time designer basically knows that what two part of a design doesn't communicate with each other, so it can just directly give this kind of a constraint in a constraint file while doing static timing analysis, which says that set false path from reg A to reg B as false. So when timing analysis tool is going to do STF for it doesn't check the path which is it doesn't check the paths which are between reg A or flip flop A to flip flop B. So that way, it can use to improve ST runtime performance. These kind of commands. There are like some other alternate command also that can be used, which can be set disable timing. So it's up to the user or up to the designer only that what kind of command it wants to use in a constraint file to let the tool know that these are the false path. Now, one important advantage which makes steady timing analysis so favorite for the designer is that it checks in worst case and best case analysis. On the other hand, dynamic timing analysis, the complexity in finding the input stimulus which produce a maximum delay, or you can say the worst delay or the best delay analysis, is quite tedious. So here it is not so feasible to do worst case and best case analysis. We'll understand this point in more depth because it's a really important feature of static timing analysis, which is whi- which helps static timing analysis to do a lot of good things. Here we are taking an example of two reg, and those two reg are connected to some with some kind of a combination circuit in between. As you can see here, we have mentioned some delay according to the lookup table that is there in the Liberty file. So as you can see here, we have mentioned on 5 nanosecond and some kind of a comment here which says that n 1.25 and 55. This basically is the PVT condition of the circuit. So it says that N basically is the process, 1.25 is the voltage, and 55 is the temperature. So it says that this 5 nanosecond delay that we are using in our analysis is under this condition when the process is normal and voltage is 1.25 and temperature is 55. So there are basically two paths, as you can see, path one and path two. Path one is constituting around 4 nanosecond of delay, and part two is having around 6 nanosecond of delay. So you can say that between flop A to flop B, we are having 4 nanosecond and 6 nanosecond. This 4 nanosecond is, you can say, is the best analysis or best delay analysis, or 6 nanosecond we can say is a worst case analysis where we are where we are checking for the longer part delay. But ideally, saying that this 4 nanosecond, 6 nanosecond, which one will violate the timing condition or the timing constraint for this path is a little tedious, because this 4 nanosecond that's coming little earlier, so it can violate whole time, and 6 nanosecond is, as it's coming little late, it can violate setup timing. But this analysis is also based on the clock that we are having and at what time this clock is coming. Now, one important feature of static timing analysis is that it can do this kind of timing analysis under all the possible conditions of PVT. There are like lot of possible combination of PVT, because in ideal condition, in actual practical condition, sorry, our chip is working in a lot of different conditions. So we have to check that under all the possible PVT condition, our chip is working. So it can have lot of combination of this PVT with this changing PVT condition. The delay of our circuits are also changing. This will lead to different worst case and different best case analysis, and it check in all the corners and report all the timing violation that it is getting. That way, it is very convenient for a designer to check that whether its design is working in every condition or not. That's how I think it's more or less we have completed most of the difference between static and dynamic timing analysis. I think this. Thank you very much.